So the structure decides the speed. But how do we talk about speed without timing it on every machine on Earth? Here is the trick. We do not measure seconds. We measure the shape of the growth. As the input gets bigger, how does the work grow along with it? That one question is big O. Let me give you 3 pictures you will never forget. In each one, you are simply trying to find a friend's name. Picture 1, a phone book sorted alphabetically. You open it right to the middle. Gone too far? Jump to the middle of the half that remains. Again and again. Each step throws away half of what is left. A million names, and you will find anyone in about 20 steps. Just 20. That is logarithmic time, O of log n, the quiet magic of halving. Picture 2. A messy pile of sticky notes in no order at all. To find one name, you simply have to read every note. Double the pile and you double the work. That is linear time, O of n. Picture 3. And this one stings a little. You compare every note against every other note to find the closest pair. 1,000 notes becomes 500,000 comparisons. That is quadratic, O of n squared. Now here is the one rule that makes the whole notation click into place. For a large enough input, the biggest term completely buries all the rest. So if your work is 3n squared plus 500n plus 9,000, we happily ignore the 500n and the 9,000. We just say O of n squared. Keep the shape. Throw away the constants. Let's lay them out as a map from the kindest to the cruelest. Constant time. Logarithmic. Linear. Linearithmic, which is n log n. Quadratic. And then at the very edge, the cliff. Exponential. 2 to the n. Want to feel that cliff? At an input of just 32, n log n is about 160 operations. 2 to the n is over 4 billion. So here is the mindset that will save you again and again. You do not optimize your way down the cliff. You design things so that you never have to stand on it in the first place.